So what I want to do today in that spirit is to start with something that's a little bit higher, vaguer and higher level, because I wanted to address this issue of what should and should not be optimized, because I think this is really foundational, not only in all the things that we're discussing here and thinking about the future, but also in the field of complex systems. And it's something to which our field has not provided a clear answer. So I want to put that out there. So I want to slay a couple dragons, and then the second part will go to something more conventional about a paper that illustrates some of these points. Okay, so this is my little group. We'd also do a bunch of applied things and so on, but I was running a bigger institute, but now I'm happier that I have people that kind of just doing research. So I want to start with this one. This is a little dragon, but since we're at a school of engineering primarily, you should kind of etch this in stone. It's very important. Premature optimization is the root of all evil. If you're a programmer or a computer scientist, you know where this comes from. But is really related, is really talking about optimization in programming and coding and so on. But it's really probably true about almost anything in complex systems, that if you optimize narrowly, whether it's in health, whether it's in a city, whether it's master planning, and we had many examples here, you're likely to goof, because these systems in some sense are required to stay open, at least in some of their dimensions. There are things that can be optimized more narrowly, but they're always contingent on some kind of slow dynamics that keeps changing things in terms of technology, values, and many other things, climate change, many other things. So this is kind of important. It means that kind of we have to be very careful about what is to be. Now, this should not be taken in a sort of nihilistic way that also says, let's not optimize anything, right? So that's what's tricky, is to start saying what really can be optimized at least a little bit, okay? And so, so what can or should be optimized in complex systems? What does nature optimize? And why, right? So I want to ask that question, so that I warned you that I was going to go there and go to a high level. And the first thing I wanted to say is, for example, here are some examples, right? So, I'm now a professor of ecology and evolution, so I have to speak this language. People talk in terms of fitness, for example, in biology. It's the central quantity of evolutionary theory. Evolutionary theory is maybe the central theory of complex systems. And so, it's often taken as reproductive success. But that's wrong, right? That's not what fitness is. The name doesn't say that. It means that the organism is fit to an environment. It's usually not used that way. But in any case, we don't know exactly what that is. Over what time scale? What aspects of the environment is it fit to? How does that actually work? We actually don't write that theory when we do population genetics or population dynamics. What about utility? So economics, a lot of us have been using that. What is it? It's supposed to be happiness or something like that. Then it became something that's sort of a formal device in economic theory. There's a famous quote by a famous economist. They call it the ether, as in physics, the ether of economics, by Ron Coase, who's a famous, orthodox economist at my institution. Or about growth, about efficiency. We heard a lot about efficiency, for example. And my point here is that, we can use these words in complex systems, but they're all borrowed. They come from other places, from economics, from biology, maybe from economics again, when we think about growth, from engineering. So I think we've not, in some sense, what I'm putting on the table for the next 10 years when we meet again, is, what exactly, we need some fundamental view about what we mean is or should be optimized, okay? So just putting it on the table. I'm not going to give you the answer today, but I'm going to point to what I think is the right direction to go. Okay, so here are just a bunch of others, right? That you could, so for example, equality, we just had a talk on that. It was a very beautiful talk, but you saw already what the problems are. Equality of what? That's a very famous paper by Amartya Sen, which is titled that, Equality of What? Inequality of What? And so he has his own answer. That was a little bit in the talk before, but it's really not a simple answer. It's kind of a complex answer. Any of these things only make sense in terms of some process that's happening and some view of what the system's doing and perhaps what its future may look like. Okay? So these quantities all bring their problems. They bring the problems that, in some sense, none of these quantities is sufficient, as I say here. If you say growth of what, inequality of what, et cetera, et cetera. Even if you say fitness or utilities, it becomes very interesting. So the big problem with those quantities, I think you all know this, but just to say it out loud, is that we don't know how to aggregate them. So for example, in biology, a big problem is when you aggregate what you might think is individual fitness into groups, people fight a lot about whether the group's selected or not. So this is a whole conversation. And the same conversation in parallel basically happens in economics. We don't know how to aggregate utilities, right? We know that your utility at some point becomes connected to mine if we need to have a conversation, but we don't know to what extent we're looking at the nation or the city or whatever, we need to consider those interactions. Of course we do, we kind of think we do, but we don't know how to build composite utilities in general. So all these problems, even if you could start taking a step, they start breaking down when you have interactions. And that's essentially the nature of it. So most of these quantities are ill-defined. We don't even know how to measure them well, as I said. We don't know how much to average them, how to aggregate them in groups, and so on. We don't know how much time to wait, fitness over what scale. Usually one thinks a generation, but that's not always true, actually. And most of these quantities lead to contradictions. So one contradiction I'll explore a little bit, which is pivotal, and it's been discussed here a little bit, is the contradiction between growth, if you will. So if you imagine what's sometimes called prosperity, if we want to be a bit more euphemistic, like, Cesar's talking about how people talk about development, and inequality. So a lot of economists, including at my institution, will tell you, if you want growth, you have to tolerate inequality. And if you want less inequality, you have to have less growth. So for example, how well do we know that that's true? Is that always true? I mean, just anecdotally, you maybe be able to compare, since we're in Switzerland, many European countries, perhaps some East Asian countries, have been able to grow maybe at least with less inequality, perhaps more inequality than they had before, but less inequality than other countries like Britain and the US. So it doesn't seem quite right, but we actually don't have a good handle when we start thinking about several things at once as to how they interact. Okay? So I hope this is in some sense all trivial, but I think it kind of goes all the way to the heart, because we've been sort of, in the last few days, at least the time I've been here, we've been talking about many things. We shut up and calculated, right? We calculated stuff, we put data in, we got data out, but I think we didn't really ask these questions at a sufficiently deep level, at least in the way I understood the mandate. Okay, so that was a little bit that part, but I want to then introduce a little paradigm. This is just the bit where I'm going to start, and then I'm going to just jump to a paper. But which is something I've been playing with for a while, and it's part of a paper that came out a little while ago and last part of my book. But it's just a simple idea. It's just a schematic, okay? But I'm going to argue, and this would be a nice thing to discuss, because many of you are at least as expert as I am, if not more. But it's just a sketch of a minimal agent in complex systems, okay? So what is an agent? What do we mean by an agent in complex systems? I do not mean an agent in an agent-based model, okay, which is usually simpler than this. But it's an interesting contrast to have that in mind. So you actually think about a little, a bacterium or an organism that's a biological organism is a better thing to think about, but very schematically. What does he have? So he needs to have a little bit of energy. It has to have a little energy reservoir, right? Because it's going to have to take actions. And it's a dissipative system, since I'm talking to physicists. So it needs to exert some forces on something. And so it needs to have a little reservoir of energy, it has to have resources. And then it needs to make the right decisions, so to speak. It needs to use that energy to get its next meal and keep going. Okay, so it needs these two quantities, which are the essential ones, since I've written a lot about information. And it needs energy, it needs information, but it needs to use it to keep going. And usually the way this is formulated is that these are internal reservoirs, if you want to call them that. There's a memory and some sort of energy reservoir, and there's an interaction with the environment. So there's sort of a phenotype, and there's a genotype, and there's a metabolism. Okay? What's interesting about this is that, so this is just very basic, okay? But now we're talking about a class of things that you could say, well, a bacterium has it, a human has it, a firm has it, a city, of course, could have it, but certainly a city government would have it, has to have money, has to make decisions, has to interact with the outside. But so you can start thinking about how this works. But what's interesting about just this point of view is that two things. One is that the energy or the material resources or the money actually is what economists call a rival quantity. If you have it, I don't have it, right? And so that creates competition and conflict. But the informational part actually has a different character. You can actually know something, and I can know something else, and we can write a better paper because of that. And maybe we could not ever have written that paper because we have the pieces but they don't talk to each other. And so information doesn't add up in the same way. And it creates essentially a force that promotes interactions. And this is basically the basis for all kinds of cooperation in complex systems. So I'm now going to tell you the story about one story about cities that has some of these elements, but it's really starting to play with these very, very basic dynamics that you can actually write down for simple systems and then iterate them up. But it means that whenever we're looking at a complex system, we need to pay attention to the dynamics of resources, which usually are dissipative, so there are resources coming in, being expended, and the dynamics of information, which mean both making decisions, which is basically using information you have, but also learning, which is acquiring new information. And in doing this, a very important element is that you have to have a model of the environment. So there's always a prospective model. You have to have a theory of the world to exist in the world and do what I described. So this is very important. This is how we're understanding now how the brain works and even how generative algorithms work, is that we have to have a model of the world in order to produce, whether it's images or actions or whatever. Okay, so that was the more theoretical part. Kai was just saying that people in complex systems are very theoretical, so there I was. But this is kind of important because when we look at many of the things that we look in data, we often don't look at it this way. We just look like with statistics and stuff. So I'm going to try to show you that even some of the things that I looked a lot at data look like this. Okay, so now sort of the second part. So, okay, this one is just more or less saying what I was saying. What becomes important is that a lot of the information is not just acquired by you or by me, it's transmitted. So we have a lot of social information that we have to take on trust, including a lot of science and things we learn, but a lot of other things. And that these environments first they become physical, but then become self-consistent. So they fight back, both in biology and of course in society even more so. So this creates all kinds of dynamics that are complicated. But again, what's going on at the same time is how well can you predict and take advantage of this environment, the informational part, and what's at stake in terms of resources. Okay, so now I want to talk a little bit about cities, and I'm going to pivot to this paper. So this is a paper I wrote a couple of years ago, and I was kind of wanting to look at all kinds of things to do with cities and urban scaling, but from the perspective not of structure of what cities are, sort of when you look at them, but from the perspective of growth, to ask about change, okay? And how much time do I have? Just want to keep track. Okay, so I'm more or less halfway through. That's good. So I wanted to just pause a little bit and this is just data, okay? And I'm showing you basically, so these are all, this is data on wages. These are American cities, metropolitan areas. You see some of them are labeled, the big ones, and this is population. And what you have here is about almost 50 years of data. So it's interesting because it's a long time, a long data set. It goes back to 1969. That's when the US started collecting this. And, it has the usual superlinear scaling and so on. That's what these black lines are, but you can follow each one of these. So you see here, for example, that Chicago and Los Angeles had the same size, more or less, in 69, but LA did better. I live in Chicago, so it's not so good. But what you see here is quite extraordinary, that all these curves are going up and a little bit to the right. So there's demographic growth and there's economic growth. But you can, these yellow points are basically the centers of these lines. So this is all in log scale. It's just the average of the log in the x-axis and the average of the log in y-axis, very simple. And then you can just put all these points on the same point. So you center the data, as it's called. And look, nothing happens. The same thing all the time. So we do this all the time as physicists, right? But it's kind of interesting because look, so if you do this, you're left just basically with the dynamics of the yellow points, which is this, which basically is telling you that the logarithm of wages and the logarithm of population are more or less following each other with a certain slope. And then you have the scaling law, which has its own structural explanation. I'm not going to get into that. That's an old story for me. And then you have the statistics of these fluctuations. And you see them here, for example, New York, how it's moving around the line, but it's not moving very much. It's very simple. Who called for that? I mean, 50 years of data in America, all kinds of crises, all kinds of stuff. If you plot the statistics of these fluctuations, you get something like this. It's approximately Gaussian, but it's not Gaussian. Okay, so this is important. The Gaussian is the blue line. And this is going to be because it's actually income, or wages is more like income. It's not accumulated variable like wealth, but it's close. And then these are basically the dynamics of each one of these variations over time. So you see that it has a lot of structure, and this is cool because it shows you some of the cities that have been doing better or worse over time and so on. So this is kind of city specific, but it's a very simple story now. It's a story about scaling, which is a structural property of basically urban networks. I'm not going to tell that story today. But then you have growth, which has to do with basically how the centers, essentially, this point goes. And then there's a little bit of, these are not fluctuations like a physicist would say. These have structure. They go over time. You see Silicon Valley and Boulder. You see the dot-com boom and bust, all that stuff. But it's kind of not running away. It's just kind of small and slow. Okay, so the point about this is that I wanted to deal with these two problems that seem somewhat contradictory, the problem of growth and the problem of statistics. So, when we write scaling laws, we all do, and so on, we just often don't take into account growth and statistics. And so when you write the scaling law this way, there are statistics, these are those fluctuations, this is demographic growth, change in population, and so on. And these are all in logs, but the way to really read the scaling law, one way of reading it, is via growth rates. These are, when you see a log, right, of a quantity, it's basically the integral of a growth rate over some time. That's what it is. And so this means that the growth rate of wages in a city is equal to the growth rate across the country plus the exponent times the growth rate, demographic growth rate of that city, and then fluctuations which come from that, okay? It's very simple. It's just a relationship, almost a sum rule between those rates, and that means that because this quantity does not depend on city size, this one could. This is what we saw the talk yesterday, that sometimes cities of different sizes don't grow at the same growth rate, so you saw that. And then this quantity also may have scale dependence. So when those quantities have scale dependence, then the growth rate can have a scale dependence, and this gives you basically a mechanism to renormalize the scaling exponents. Okay, so it's kind of cool because it introduces scale variance potentially, and it gives you a way to control for that. So now I just want to spend my last 7 minutes, more or less, and just showing you about some of these. I'm going to go a little faster. There'll be a lot more math, but just basically to say there's still a problem when you think about wages having statistics that looks more or less log normal. So it would be normal in log variables like I showed you, but with some corrections. I'm not going to show you today where the corrections come from. You can look at the paper. But this usually comes from a multiplicative random process. That's usually the simplest model by which something grows. So that means that something like resources, this would be wealth, is growing at some growth rate times resources again. And this is made out of income and costs. But this difference here is not guaranteed to fluctuate independently, to have nice statistics. It could be very messy, right? So what you need to show, basically, is that incomes and costs become correlated because basically people have to maintain a budget. So this becomes basically a control mechanism, but I want to show you a couple of things. One of the things is that when you integrate that equation, you get something like this for the actual observed growth rate. This is just because it's a multiplicative process. We heard yesterday about stochastic integration. This is Ito integration, but there's a correction to the growth rate that comes from fluctuations. And this is important. So I'm not going to get into this, but this solves that equation completely, and you can see all the statistics and so on. And what happens with that equation is that when you take it across scales, on the one hand, if the growth rates become scale dependent, you correct the exponents, so the structure is not maintained. A scaling law basically has the form that it has because it's expressing an invariance of exponential growth over time under certain conditions. So when that's broken, you have corrections to exponents. And on the other side, you have basically the kind of statistics which have to do with log normals and distributions of incomes and so on that we're familiar with. So this is my main point for this part of the talk, which is that when you actually look at just something very simple like this, that's growing, but it has fluctuations, okay? This is like the economy. Then you have two quantities to focus on. One is basically the average growth rate, and the other one is called the volatility, but basically the fluctuations. And the point is that these two things require these two things now, what we want to do is to look at them, like look inside and see what they're made out of, right? And the point is that they're made out of mechanisms that are essentially contradictory. They're pulling you in different directions. And again, there's stuff in your book and so on that's very related to this. I'm telling the story in my own words, but they're kind of curious. So the growth rate has to do essentially with growing resources. You have to make good decisions. You have to have knowledge and information. That's also more or less without formalizing the message the economists tell you. But the volatility requires control. It requires that basically you can take care of crises. You have to have money saved. You have to basically deal with basically evening assets over time and keeping things, predictable. And the point is that what people do is precisely that. The reservoir of energy allows you to deal with this, but the innovation, the learning deals with this. Yeah. So what you have is that in terms of times they're very uncertain, you want to control this, and in terms, because you want to make this quantity big, and in terms of they are calm, you want to innovate. Typically, you need to do both at the same time. So I'm going to skip some of this in the interest of sort of time, but just leave it here. So basically, this gives you a very simple phase diagram. This can be elaborated. These things have other dependencies. But basically, to have growth, you have to be above these red lines, which depend on the growth rate and the volatility. And this basically means that you learn, you go this way. You risk pool, you go this way. And the condition often of being sort of in a very unstable position here at low growth rate is the position of poverty. I'll show you a couple plots. And what it means to be here is basically to have high growth rates and maybe high fluctuations is more like a startup, a sort of a very exciting environment, but very unstable. Okay, so this is, for example, showing you that people are poor. This is from financial diaries and shows you that people that typically poor have a lot of financial uncertainty. This is not always the case, but it's typical, certainly in cities. So the volatility is actually often a sign, it's something that destroys your capacity also to develop assets and so on. Okay, so this part now is to be expected. I'm not going to show you this, but it's basically that you can develop control mechanisms by which essentially you build a pool of money, you can adjust your spending, and this happens basically in a way that can allow you to control the fluctuations, bring the volatility down, but it means that basically you have to have money or some resources saved. So that buffer becomes very important and becomes sort of a public buffer as you go to higher scales. So it becomes things like contracts that give you a wage, insurance, which is typically a private mechanism, but also a number of other public mechanisms that when people are poor, they require that buffer to be a public instrument. For learning, I'm not going to tell you a lot about, but I'm going to say basically that the idea is that to multiply resources, you have to coordinate your choices with the environment. This is why it's information about the environment. And when you average this over time, there's several important papers in statistics and then in gambling and in information theory that derive this. Basically, it means that the average growth rate becomes essentially something like this, which is nothing else than the information that the agent has about the environment. But remember, this is the degrees of freedom in the environment that give you energy, they give you access to resources. It could be about other things, but they have to be about that. Okay, so the point about this is that when you think about information and you aggregate different sources of information, they typically add non-additively. So this allows you to have people that do different things, to actually come together and solve more complicated problems. And this is typically something that markets only do to a limited extent. I'm not going to show you that, but this is why you need to form organizations, universities, firms, and a bunch of other things. And this also has manifestations in terms of, creating redundancy from a point of view of a predator. So this one's for discussions we were having about this, but also to combine information, as we said, in terms of creating a bigger picture like synergy. So these are different kinds of collective behavior that combine information in different ways to create different adaptive dynamics. So there's a lot that unfolds from these simple principles. So I'm not going to show you this, but this is kind of one of my last slides, is that you can combine all this to basically disentangle these two problems. The problem of how you create growth, which has to do with knowledge, and how do you reduce inequality, which has a lot to do with the dispersion in these growth rates and maybe compensation so that people that are in positions with fewer resources can get higher growth rates. It means that they have better information, or they have some other access to that so that their resources can grow faster. That can basically compensate for how the distributions would normally change over time. So there are ways that now that you have more dimensions, you can start understanding these these various degrees of freedom. You can start optimizing various things in order to create more complex behavior. So thank you.